Welcome back, everybody. This is Dr. Jacobs, and this week we are going to learn about the analysis of variance. By the end of this unit, there's several things that I want you to be able to do. I want you to be able to determine when to use an analysis of variance, also known as the ANOVA, to analyze data. I want you to write the research and null hypotheses in symbols and words to fit the research question. I want you to be able to check the one-way ANOVA assumptions to determine whether we meet or violate the assumptions. And if we violate those assumptions, if our analysis is robust to the violation. I want you to be able to calculate and explain the meaning of the ANOVA test statistic. I want you to find the correct critical values of the ANOVA based on the research question, alpha level, and data set. I want you to be able to write and interpret the results for the ANOVA. I want you to be able to calculate, interpret the relevant follow-up analyses for the ANOVA. And then I want you to use the hypothesis testing steps to run an ANOVA to analyze a data set. All right, so let's have a little bit of a short review so it gives us a little bit of a rationale why we even need another analysis. So up to this point, what is the greatest number of means that we could test at one time? So far, the most that we can test at one time is 2 sample means. Okay, so t-test review. In the t-test, we only examine the differences between 2 groups. One of the examples I used was if we wanted to examine the differences between the exam scores, which is our dependent variable of my online section of this course versus my face-to-face section of this course. So my independent variable is method of course delivery. So either you're on my online or you're in my face-to-face class. And so in this example, because there's only 2 means, you only have to do one test. So you compare the first sample's mean with the second sample's mean to see if there's any statistically significant differences. In this example, my independent variable had 2 levels. It had 1, which was my online class, and 2, which was my face-to-face class. In stats, the levels of the independent variable are represented by lowercase italicized k. So make sure that goes on to your handy dandy symbol sheet. Okay, so let's practice with this for a little bit because there actually gets to a point in statistics where you have more than one independent variable. At this time, we've only had 1 so far, but there may be more levels to it. So let's practice. So example, a teacher wants to test how many words students read correctly per minute after being exposed to 1 of 3 conditions for 1 month in addition to regular reading class. She places different students in each of the conditions through random assignment. Okay, so treatment conditions. Students in this condition read aloud for 30 minutes each day in addition to regular reading class. Students in this condition read silently for 30 minutes each day on their own in addition to their regular reading class. Students in this condition do no extra reading in addition to regular reading class. All right, so while we're looking at this example, what would our dependent variable be? So the dependent variable, if we remember, is the thing that we're measuring in whatever our study is. So in this situation, our dependent variable is how many words our students can read correctly in 1 minute. Okay, so then what would our independent variable be? Our independent variable would be the different treatment conditions. So in this case, the different reading conditions. So then how many different levels are there to our 1 independent variable? There's 3 because there's 3 different groups. So testing 3 means, the problem is if you increase to 3 means, right? Because that's substantially different than just having 2. How many t-tests would we have to do to see if there's any differences between any of the different means? So we remember we would use the independent samples t-test to test the differences between 2 samples composed of different participants, so using a between group research design. So here we would actually have to conduct 3 different t-tests, okay? We'd have to compare the mean of group 1 with the mean of group 2, the mean of group 2 with the mean of group 3, and then the mean of group 3 with the mean of group 1. So let's take that even a little bit further. What if we had to test 4 means? So how many comparisons would you have to do if you increased it to 4 different groups? Try to figure this out before moving on in the lecture. You would have to do 6 comparisons. That's a lot of t-tests, right? So you'd have the mean of group 1 with the mean of group 2, the mean of group 1 with the mean of group 3, the mean of group 1 with the mean of group 4, the mean of group 2 with the mean of group 3, the mean of group 2 with the mean of group 4, the mean of group 3 with the mean of group 4. And so that's a ton of t-tests. You literally would have to run 6 different t-tests to be able to do all these comparisons. So why would it be an issue to conduct multiple t-tests like that? Think about this really hard before we move on. So remember, when we conduct one, let's just say independent samples t-test, because that's the t-test you would use to compare 2 group means or 2 sample means with a between group research design. So when we do that, we set our alpha level, which is the threshold, the amount of risk we're willing to take to make a type 1 error. So the alpha level that we typically use for this class is 0.05. And if we were using computers to calculate a p-value, remembering that our p-value is the probability that we're going to make a type 1 error if we reject the null hypothesis with the test statistic that we have. So we always have to make sure that that probability of making a type 1 error is less than our alpha level or our threshold or our cutoff. Okay, so anytime that we conduct another analysis, we actually increase the chances of making a type 1 error. Okay, and if we remember back to our probability unit, we saw how when you added things to it, that it like if we're doing different combinations of numbers for the lottery, and things, that it could go back and edit this part out. So when we see here, we have the probability of a type 1 error increases as the number of statistical comparisons increases. So when we compare 2 means, and if we have an alpha level 0.05, we see that's just the probability of making type 1 be 0.05. If we increase it to 3 means, however, we see then that the probability of making type 1 error goes up even further. It's 0.143. And then when we have 4 means, we see that the probability of making a type 1 error is 0.265, which is 26.5%, which is a 1 in 4 chance that we're going to make a type 1 error. So if we're comparing that many analyses, likely one of our answers will have a type 1 error. And we see it dramatically goes up as we increase the number of means that we're comparing. Okay, so for this reason, they developed an analysis called the ANOVA, and the ANOVA has, there's several different types of ANOVAs. And typically after an introductory stats class, the next type of class would probably be either an entire semester on different types of ANOVAs, or an entire semester on something called regression, which is also something that we'll start learning this semester as well. And so instead of doing all these different comparisons, they came up with this type of analysis that allows you to compare all of the means at one time. And so, like I mentioned, there's a whole bunch of different ANOVAs that you can find. And so because there's so many different types of ANOVA, we have to learn how to name the ANOVAs, or when we hear different names of ANOVAs, we know exactly what they're doing. So usually when we say what type of ANOVA that we're doing, it comes in 2 parts. First, it identifies the number of independent variables. The number of independent variables is very different than the levels of an independent variable. So for example, if I wanted to see if there were significant differences in the amount of sleep that people got, and we wanted to compare gender identity. So gender identity could be one independent variable, and we might have, so there would we have man, woman, non-binary, gender fluid, and we could also have others. So we could say that gender identity might have 5 levels to it. And then we could also maybe compare grade level, right? So if we compared if we had a grade level in there, there could be, if we're talking about high schoolers, there could be 4 levels to that independent variable. But if we were comparing sleep habits based on gender identity and on grade level, we see that we have 2 independent variables, and each of them have different levels to their individual independent variable. Okay, the second part is identifying the type of research design, and this is something that we started learning in week 1. So for example, if we have a one-way between groups ANOVA, we have one independent variable, and we used a between group research design with that ANOVA. If we remember what that means, it means we have different participants in each level of the independent variable. So again, number of IVs, when there is one independent variable, we call this a one-way ANOVA. When there's 2 independent variables, we call it a two-way ANOVA. I wonder if you could guess what it would be for if we have 3 independent variables. You're correct. It would be a 3-way ANOVA. You got this. So research design again, when naming ANOVAs, we use the independent samples or independent, so between group design, we'll call it a between group. So if we remember, we use independent samples when we use a between group research design. This is where each level of the independent variable is made up of different participants. For example, you can have a one-way between group ANOVA. When naming ANOVAs, if we use dependent samples, this is often referred to as repeated measures. So we use dependent samples test when we use a within group design where the levels of the independent variable are made up of the same participants, or a matched group design when we assign participants to a level based on specific characteristics such as IQ scores. So for example, you may have a one-way repeated measures ANOVA. So let's practice. What would you call an ANOVA that was examining the mean differences between males, females, and intersex people of all of the 9th, 10th, 11th, and 12th graders on their ACT scores at Jefferson High School during the 2012-2013 school year? So let's first start by identifying our independent variables. What's our first one? We have biological sex, which had 3 levels, male, female, and intersex. And then we also had grade in school, which had 4 levels to it, 9th, 10th, 11th, and 12th grade. So here, are these independent samples or dependent samples? These are independent samples. That's because we have different participants in each level of the independent variable. So what would we name this ANOVA? This would be a 2-way between group ANOVA. All right, so now that we made it through that, let's practice by reviewing the hypothesis testing steps. What's our first one? First one is determine which statistical analysis to run. What's our second one? We're going to write out our research and null hypotheses in symbols and in words. What's our third one? We're going to check our assumptions to make sure that we can do the analysis. What's our fourth? We're going to use that formula to calculate our test statistic. What's our fifth one? We're going to find our corresponding critical values. What's sixth? We're going to make our decision. And then what's 7? We're going to conduct any relevant follow-up analyses. All right, so let's go ahead and get started. So our first step is to determine which statistical analysis we want to run. So we're going to specifically examine the one-way between groups ANOVA for this unit. And this is when we have one independent variable with 3 or more levels, and it's utilizing a between group design. Okay, so with this, we use a one-way ANOVA when we want to compare the means of 3 or more samples utilizing a between group design. Warning, so the ANOVA is called what we call an omnibus test, and this means we are actually not able to identify which means are significantly higher or lower than the other means. So when we do this analysis, we just say that if we find that we have significant results, we just are saying that one of our means, at least one of our means, if not all of them, because we don't know which ones, are significantly different from at least one other mean that we're testing. So if you find significant results or our p-value is less than our alpha level in step 6, we would have to do some follow-up analyses to see which groups were significantly different from which ones. All right, step 2, then we're going to write out our research and null hypotheses in symbols and in words. So in ANOVAs, we're testing 3 or more means, which means we have to include a mean for each of the groups that we're including in the analysis. Okay, so when we write our research hypotheses, it's going to be a little bit different than what we've seen in the past when writing our hypotheses. We're going to use a symbol called the not symbol, so it looks like this, and that will indicate that our means are not equal. So you're going to want to put that not symbol onto your symbol sheet. All right, so if your independent variable has 4 levels, your research hypothesis would look like the following in symbols. So we have H sub 1, which is our first research hypothesis. We're going to put a colon to let everyone know that our research hypothesis is coming. Then we put the not symbol, and then we'll have our means all equal within the parentheses. And so what this is saying is that this statement is not true, that all of the means are equal to one another. So pro tip with this, you have to match up the number of means that are in your like whatever your research study is. This is just an example. If we had an independent variable that had 4 levels to it, if you had an independent variable that had 10 levels to it, you would have 10 different means. If you had an independent variable with 3 levels to it, you would just have 3 means listed there. Okay, so in words, the template would look like this: research hypothesis, and then you put a colon. One sample mean is significantly different from at least one other sample mean. And so we remember from our previous lectures that when we have these templates, we actually have to put in our independent variables and our dependent variables into it in order for it to be right. So you do not just write the template when doing this. You'll actually have to go in and put in your independent and dependent variables into it to make it work. So then we remember from what we've done so far, our null hypothesis has to cover everything that our research hypothesis doesn't cover. So if our independent variable has 4 levels, our null hypothesis would look like this in symbols. We'd have H sub 0, which represents null hypothesis. Then we have the colon, which is letting us know that our null hypothesis is coming. And then here we see that we have all the means are equal to one another. All right, so in words, our template would look like this: null hypothesis, then put a colon. There are no significant differences among the sample means. We remember that this is just template. We would have to insert our dependent and independent variables into it to match up with whatever study that we're doing. So then our next step is checking our assumptions, and none of the assumptions that we're doing in here will be different than what we've done before. So here I have this table where it summarizes what we're doing. The very first one you're always going to want to check is our dependent variable measured on a scale? So that means if our dependent variable is not measured on an interval or ratio level of measurement, then we violate this assumption. If we violate the assumption, then we typically move on to see, hey, okay, if we violated the assumption, can we still do this analysis anyway? And for the one-way ANOVA, that's not true. So you cannot continue and go ahead and do the analysis anyway if you violate this assumption. You have to go find whatever the non-parametric equivalent was of this analysis. Our second one that we're going to check is that our data set is free of significant outliers. And so the way that we do this is we calculate z-scores for each of our x values. And we do that by groups. So if we had 3 different groups, so if we're looking at those 3 different reading conditions, we'd look at, I'm going to make this up because I'm not exactly sure this is what it was, but it was like read out loud for 30 minutes group. So we'd find the mean of that group, the standard deviation of that group, and then we would calculate z-scores based off of those numbers for that group. Then we'd move on to the reading silently for 30 minutes group, and we do the same thing. We'd find the mean of that group, standard deviation of that group, and calculate the z-scores for everyone with relation in that individual group. And then we'd move on to the third group, which was, I believe, no extra reading outside of class. We'd find the mean of that group, the standard deviation, and then calculate all the z-scores for that group individually. And so if any of those z-scores are plus or minus 3.29 or beyond. So on the positive side, that's if it's 3.29 or higher. On the negative side, it's negative 3.29 or lower. If any of those z-scores are that, then it's an outlier and we violate this assumption. So if we violate the assumption, then we move on to check to see if our analysis is robust to the violation. And it would be, our one-way ANOVA would be robust to the violation of this assumption if we remove the outlier before running the analysis. So anytime that you remove data from your data set, you need to write it in your manuscript why you removed it and how many you removed, because we don't fabricate data. That's it's super unethical. So you would say, okay, I moved 3 data points or 3 participants' data from the analysis because they were outliers, because they had Z-scores that went beyond plus or minus 3.29. Okay, then after you check for outliers, I would check for normality. And then so when you're running this in software, it's a really easy way. You'll just go in and you'll hit some buttons and it'll pop out the p-values for our Shapiro-Wilks test. It'll do it for each of our individual groups. So with the reading condition example, you would get one for each of those individual groups. If our p-value equals or is greater than 0.05, we meet the assumption. If we meet the assumption, we don't have to check if it's robust, right? We just move on to the next assumption. However, if we violate that assumption, then we have to check and make sure that we can still run the analysis anyway. And for the one way between groups ANOVA, we can go ahead and run the analysis anyway, as long as our sample size is 30 or more. So then our fourth assumption is homogeneity of variance. Sometimes you hear this referred to as homoscedasticity. And this is when we say that the populations being studied have approximately the same variance. The way that we test this is we do something similar to what we did for normality, but for homogeneity of variances, we look at the p-value for something called the Levene's test. And if the p-value for our Levene's test is greater than or equal to 0.05, then we meet the assumption. If our p-value is less than 0.05, then we violate the assumption. Now, if we violate the assumption, our analysis is robust to the violation of the assumption as long as the larger group variance is not 4 times or more larger than the size of the smallest variance group. And the way that you would figure that out is you would take the variance of the largest variance group and literally divide it by the smallest variance. And if that number is less than 4, you're good to go. If not, you can't run this analysis. And this is slightly different than what we saw with the independent samples t-test. So it's really important to keep those separate. 5, we've seen this assumption before as well. This is independence of observations. This is just saying that one participant doesn't influence another participant. And if we are using like a between group design, like we are with a one-way between groups ANOVA, that the groups are influencing one another as well. Now, if we violate this assumption, we can't run this analysis. And likely, I don't know how you'd run any of the analysis for it. Our last one that we check is random sampling. This assumption is that we selected our sample from the population of interest using random selection. So if you use random sampling, then yes, you meet this assumption. If you didn't, then we need to check to see if it's robust to the violation of the assumption. And we can still do the one-way between groups ANOVA as long as we don't generalize the results from our sample back to the population we're interested in studying, and as long as we write this as a limitation in our research manuscript. That leads us to step 4, calculate the test statistic. This is actually significantly more difficult with this analysis than other analyses that we've had in the past. Okay, so the test statistic for the ANOVA is going to be the F-test. So if I asked you, what is the test statistic for an ANOVA, you could tell me F or F-test. The F statistic tells us how big the difference between the groups are in comparison to the differences within each of the groups. So an F statistic of 1 indicates there's no difference among our means. And that's what it looks like. So we're going to be looking at something called our between groups variance, and we're going to divide it by our within groups variance and see if there's significant differences. Because what they're saying is that if there's really difference between our groups, then they shouldn't all overlap, right? There should be a big enough difference that it's not the same of what we're seeing within our individual group. Okay, so like I mentioned, this is going to be significantly harder to calculate, and I'm going to read you these steps. Don't get overwhelmed right away. We will have a whole bunch of tables to walk through this together, but I wanted to kind of give you a preview of where we're going. So first, you're going to calculate these 3 different numbers. Each of them are actually going to have their own little table that we go through. So you're going to calculate the sum of squares within. The symbol for that is going to be SS sub within. So go ahead and put that on your handy dandy symbol sheet. Then we're going to have the sum of squares between, which our symbol for that is going to be SS sub between. And sum of squares total. And for that, we'll have our symbol as SS total, subtotal. Then you're going to calculate your degrees of freedom within and your degrees of freedom between. So we'll see here that we have two different types of degrees of freedom that we're going to calculate. Then we have to calculate our mean squares within and our mean squares between. And then we'll finally get to be able to calculate our F statistic, which is symbolized by capital F. So you want to make sure that you snag all of these different symbols on here for the sum squares within, between, and total, degrees of freedom within and between, mean squares within and between, and then the F statistic symbol. So you'll want to write all of these onto your handy dandy symbol sheet. Okay, so warning, danger ahead. It's really hard to calculate this. It's a lot harder than what we had with the t-test because there's a lot more going on with it. It's going to be super important that you organize your work. I should be able to, like, if this ends up being something that's on your calculation assignment or another assignment for this class, I should be able to really easily find where all of the work is. And I think, like some of y'all have seen that if you make one mistake, if I see your work, I'm able to go in and not take off as many points for the whole thing. Because this is one of those things where if you make a really tiny mistake in the beginning, it could have really huge differences by the time we get to the end. Okay, so we'll use something called a source table that we'll talk about in a little bit, and some other tables to keep everything organized. But first, we have to learn about something new. So when we're doing an ANOVA, we're going to learn a new concept that's called the grand mean. The grand mean is represented by the symbol X with two bars over the top, or sometimes people represent this by a capital G, capital M. So the grand mean is the total mean for every observation in the sample overall. Okay, so when we're calculating an ANOVA, we'll actually find the mean for each of our individual groups, but then we need to also find the grand mean, which has every individual data point for all of the groups combined into one. So why can the symbol that has X with two bars on top be confusing for students sometimes? It kind of looks like our symbol for sample mean or mean of a sample, which is X bar. So you just have to be really careful when we're looking through our different formulas and when you're calculating things. And if I were to ask you what X with the two bars on top was, you'd have to be able to tell me that it's grand mean. The way that I remember is that it's really, this mean is very grand. It's like a king. It's got a crown. It has its two little bars on top. And so that kind of helps me remember the difference. So here are all of our formulas in this table. I'm going to walk through we're going to go through each of these individually, and you'll see where we put our answers. So the ANOVA has a really interesting way of showing its results. So in the past, we've written our results in words in our two decisions. If we remember, either we're going to reject the null hypothesis or we're going to retain the null hypothesis. Okay, and then we also had a way where we write it in symbols, where we use just the symbols for each of the things. So with ANOVA, we do all of that, but we also are going to put all of our results into something called a source table. And so here, if we were writing our source table, we'd have this table, and in place of where it says S, like for example, in that cell where it says SS sub between equals, and then the summation, open parentheses, X bar minus the grand mean, close parentheses squared, instead of having all that font there, we'd actually just have a number. So what we're going to do is go through each of these. You'll notice at the bottom of this slide that 1 star means that our F statistic is significant at the 0.05 alpha level, and then we'll see 2 asterisks will mean that it's significant at the 0.01 level. We actually will use both of those alpha levels when we're doing the ANOVA, and we'll get there when we get there. So let's first start out by finding our sum squares between. All right, so I'm not going to make you work this out right now, but if we're looking at this, and I am not exactly sure, let's say that we had some sort of reading intervention where one group had to read 0 extra minutes a day, one group had to read an extra 15 minutes out loud a day, and a third group had to read an extra 30 minutes out loud every day. And so if we're looking at this, to calculate our sum squares between, we have all of those X values. We first have to go and calculate the mean for each of the groups. So we see the mean number of words that group 1 read in a minute was 22.25 words a minute. Group 2, it was 41.50 words per minute. Group 3 had average word per minute of 51 words per minute. Okay, so here when we're calculating our sum of squares between, we're going to take each of our group means and subtract it from our grand mean. So for group 1, the 0 minutes, we see that our mean for that group is 22.25. So we take that and we subtract it from the grand mean. And we actually do that for every single X value. So it can be kind of confusing because sometimes people, if I give homework like this, they'll try to only put it in that first column or that first row for group 1, where it has that -16 as the answer, but forget to put it for each of the places where we have participants. And if you do that, then that's going to give you the wrong answer. And then we see we do the same thing for group 2. So for each individual X that we have the group mean, which is 41.50 minus the grand mean. And then we do the same thing for group 3. Now, when we're doing this, we'll see when we calculated the grand mean at the bottom of that table, it has the X with the 2 bars equals the summation of X divided by N equals. We actually go through and add all the individual X's. Although in this example, each of our groups only have 4 participants, that's not always true. These groups aren't always going to be even. So you can't just go in and take the mean of the means to do this. You literally have to go in and just add up all the X values for all the participants in the whole study, and then divide by the sample size of all the participants in the entire study. Okay, so then we continue. And just like we learned when we were doing things earlier in the semester, we have to go in and square those deviation scores. And then to get the sum of squares between, after we square the deviation scores of the mean minus the grand mean, and we add them all up to get the sum square between, which we see for this is 1,716.48. So then if we're going to go put that into our source table, we see that we eliminated the whole formula and just went ahead and threw it in there. So I just kind of want to walk through it step by step so that you don't get nervous about all the different steps that we have here. Okay, so then when we're doing sum of squares within, this is just kind of that typical thing that we've been doing almost this whole time. The only difference is when we're doing sum of squares within, we're looking at our deviation scores within each of the groups. So for group 1, the 0 minute group, and we found our mean for that. And then what we're doing is taking our individual X scores and we're subtracting the mean from that for that individual group, okay? And then we'll do that for group 2 as well. So we'll go and we'll find our mean of group 2, and then we'll take X minus whatever that group mean was, and we'll find that score. Then group 3, we'll do the same thing. We'll find the mean of group 3, and then we'll take X minus the group mean and find all of those. So then we have to go, like we've done almost every other time with our deviation scores, we have to go in and square those. And then when we add up all of those squared deviation scores, we get our sum of squares within. So then we see that value is 21.74. We can go ahead and go in here and substitute the formula for the number that we calculated. That leaves us last with our sum of squares total. And the way that we calculate this is we take each individual X value and we subtract the grand mean from it. And so that's slightly different. So we go ahead and find those scores. Then we square those scores like we see in that last column. And then when we add all of those up, we get our sum of squares total. And although that we don't need necessarily use sum of squares total to calculate our F statistic, it's something that does go into our source table. And then also it is something that we use later on when we're doing some follow-up analyses as well. All right, so we see our sum squares total was 1,738.22. So we would go ahead and put that into our source table. And then we'll see that we're going to move on to calculating our degrees of freedom. And so for the one way between groups ANOVA, we have 2 different types of degrees of freedom that we're going to calculate. We have something called a degrees of freedom between. And to find this number, we take the number of groups that we're comparing and we minus 1. In other words, we take the number of levels of independent variable and we subtract 1 from it. All right, so df between equals k minus 1. Then for our degrees of freedom within, which is our second types of degrees of freedom that we're learning, we have to find the degrees of freedom for each of the individual groups that we're testing, and then we add all of those together. So here, for group 1, let's say, we'd have degrees of freedom sub 1, which means the degrees of freedom for group 1. We have the sample size of that group minus 1. So if we have 3 different groups, we would do 3 different degrees of freedom for each of them, and then we'd add those numbers together. If we had 4, we'd do it 4 times. If we had 5 groups, we'd do the degrees of freedom for each of the 5 groups and then add all together. So we go to the example that we had 3 different reading conditions. So our degrees of freedom between is 3 minus 1, which equals 2. In our example, we have 3 groups of 4. So you'd find the degrees of freedom for group 1, which is 4 minus 1, the degrees of freedom for group 2, which is 4 minus 1, and the degrees of freedom for group 3, which was 4 minus 1, and we added those all together to get 9. So then we'd put those numbers into our source table where they would go. And slowly our source table is not looking as scary as it was when we first started. Okay, so then we go and calculate our mean squares, and it's actually not super hard to calculate the mean squares. We just take our sum of squares. So for mean squares between, we take our sum of squares between divided by the degrees of freedom between, and that gives us our mean squares between. We do the same thing to get the mean squares within. We take our sum of squares within, divided by the degrees of freedom within, and that gives us our mean squares within. So we go through and work that out. And then we put those numbers into our source table. And that leaves us with one thing that we need to calculate, which is the F statistic. And all we need to do that to find that is take our mean squares between and divide it by our mean squares within, and it'll give us our F statistic. So here we see that our F statistic equals 354.64. And then we would take that number and go ahead and throw that into our source table. And so our source table is not 100% complete yet. Our numbers are in there. We still haven't determined whether we're going to reject or retain the null hypothesis for an alpha level of 0.05, and then also for alpha level of 0.01. So our source table is not complete quite yet. And that is because we have to go in and find our critical values now. All right, so step 5, we're going to find our critical values for both the 0.05 and 0.01 alpha levels. And then ANOVA, you'll have multiple degrees of freedom, which we learned to calculate already. And we're going to use those to find our critical values at both the alpha levels of 0.05 and 0.01. And so I have provided a F critical value table for you to use. And you'll use this for the ANOVA rather than using the T critical value table, which was used for our T test. All right. So again, we're going to use that degrees of freedom between and our degrees of freedom within to do this. So this is what the table looks like. What you do is you intersect the degrees of freedom between with the degrees of freedom within to find your critical value. So with this example that we've been doing, our degrees of freedom between was 2. So we found that at the top. And then we take it down to the row that had a degrees of freedom within of 9. And we found that for this, that we'd have a critical value of 4.256 for an alpha level of 0.05. And then we replicate that with the table for an alpha level of 0.01. So at the very top where it says F distribution table, FCV table for alpha level of 0.05, you're going to want to pay attention to what the alpha level is. So if you print off the tables that I've provided for you, you might want to highlight what that alpha level is so that you pay attention to what it is. So then we replicate the same thing, and we see that we have a critical value of 8.022 for an alpha level of 0.01. So then we will use those to make a decision in step 6. You'll notice that when we're comparing our test statistics, that we're actually going to have a normal curve that looks a little bit different than what we've seen in the past. If our test statistic exceeds our critical value, we reject the null hypothesis. If it doesn't exceed the critical value, then we retain our null hypothesis. So for the ANOVA, we're going to do this for both alpha levels of 0.05 and 0.01. And again, the normal curve is going to look a little bit different. We'll see we only have one side on this, and that's because if we remember, we cannot identify which group is going to have a higher mean. We're just testing to see if there's a significant difference somewhere in between all the means that we're comparing. And so what we'll see is that we'll have our line, we'll have one tail of our normal curve will hit kind of where the y-axis is, and then we'll have it go only one direction. So then when we're making our decision and writing results, we'll use a source table, but it'll actually have the values that we had previously. And then what we'll do is we'll draw out our normal curve for both an alpha level of 0.05 and an alpha level of 0.01. So you'll have two curves. And then if it's significant at the 0.05 level, you'll put one asterisk by where that F statistic value is. And if it's significant at the 0.01 level, we'll have two asterisks. That's because if our F statistic is significant at the 0.01 level, it will always also be significant at the 0.01 or 0.05, sorry. So this is what it looks like. So you'll see here we have our two normal curves. One's for alpha level 0.05, one is for an alpha level 0.01. We have to label both of our regions. We have our retain the null hypothesis region. We have our reject the null hypothesis region. We have our critical value, which is the boundary that separates our two decisions that we can make. We remember that our F test statistic value, the one that we calculated in step 4, we have to label that as well. And it has to go beyond our critical value in order for us to have significant results. And so when we're looking at both of these for alpha level of 0.05 and 0.01, we see that our F statistic is way beyond our critical value. So what we find here is that we have statistically significant results at both the 0.05 and 0.01 alpha levels. So what we need to do then is go to our source table, and then we would put two asterisks by our F statistic to indicate that it is significant at the 0.05 and 0.01 levels. Now, if we looked at this and pretend that we retain the null hypothesis at the 0.01 level, but it was significant at the 0.05, we would have just had one asterisk by our F statistic. Now, if we don't have significant results, there would be no asterisks at all. So if we have statistically significant results in step 6, we move on to step 7 and conduct our relevant follow-up analyses. There's a couple of different types of follow-up analyses for the one-way between groups ANOVA. One's going to be our effect size, and our second one's going to be Tukey's honestly significant difference. I always laugh at that one because anytime like someone's like, I'm the honest company, or honestly, I automatically think they're lying. So I kind of giggle at that. Our symbol for Tukey's honestly significant difference is HSD. You'll want to include that onto your handy dandy symbol sheet. So it makes sense that we don't conduct post hoc analyses if there's not statistically significant results in step 6, because that means there's no differences. So we don't need to see how big the differences are, or how meaningful they are, or which one is significantly different because they're not. So our effect size for the ANOVA, we're generally going to calculate R squared. And this effect size is the proportion of the variance in our dependent variable that is accounted for by group membership. So it's saying the variation that we're seeing in our data set seems to be accounted for by whichever, by them being in different groups. Okay, so the way we calculate R squared is we take that SS between that we calculated earlier and divide it by the sum squares total that we also calculated earlier. And if that number is 0.01, once it gets to 0.01, we say that's a small effect size. If it gets to 0.06, we say that's a medium effect size. And if it gets to 0.14 or larger, we say it's a large effect size. So then we get to Tukey's honestly significant difference. This is a post hoc analysis or follow-up analysis that allows us to make comparison across different pairings of means. So we know that the ANOVA, we can't say that one group's bigger than another. We can just say that all of our means are not equal if we reject our null. And so we have to use Tukey's honestly significant difference so that we can try to find out which means are larger or smaller than the other ones, and if those are significant differences. So Tukey's HSD uses the Q test to see if there's significant differences between the different means. You would do this for and compare two means at a time for all of the different combinations of means. So you'd use another critical value table, the Q table, along with degrees of freedom and alpha level to find the critical value for Tukey's HSD. So note that in the Q table, the sign doesn't matter, only the magnitude or size does. So what would it mean if doing these follow-up analyses, these Tukey's honestly significant difference, we found a significant difference? This would mean there's an honest difference between the means being compared. Okay, and so the way that you do this is you have to calculate your standard error. And the way we do that, it's the square root of our mean squares within divided by our sample size. And then to do Tukey's HSD, we have a formula where we take the mean of whatever. So if we're comparing, let's say, the mean of group 1 and the mean of group 2, and we want to see if there's a significant difference between those two groups, we'd subtract their means from one another and then divide by that standard error. And then we'd put that, if we look in our table, Tukey's HSD, you put in a table. And so you would enter whatever that calculation is there where it has group 1 mean intersects with group 2 mean. And you would do it for all the different comparisons that you were wanting. All right, so that's all for this week. I know it's a lot. You can review this lecture as many times as you want. If you have any questions, feel free to come in. If you're wanting to study or just ask questions, please make use of my office hours. It's been really nice meeting some of you in office hours and the questions that you had. And if we need to set up like a Google Meet or something, we can do that as well. So I hope you have a great week, and I'll see you next week.